Gentlemen and ladies, start your engines. We are about to do our first calculation, the forward pass. And I want you to know, despite its slightly ominous name, this is one of the most satisfying calculations in all of engineering. Because at the end of it, you will know exactly how long your project is going to take. There is something almost magical about that. The goal of the forward pass: find the early start and early finish for every activity in the network. We move from left to right chronologically, and we fill in the top row of every node. The formula: EF equals ES plus duration. That is it. That is the entire forward pass in one equation. If you know when an activity starts, and you know how long it takes, you know when it ends. Look at our example. Activity A, site clearing, starts on day 1. It has a duration of 10 days. So its early finish is 1 plus 10, which equals 11. The dashed blue arrow then transfers that early finish of 11 to become the early start of activity B, footings, which starts on day 11 and runs for 9 days. What is the early finish of footings? Day 11 plus 9 equals day 20. The cheat sheet in the corner explains the logic in plain English. The contractor starts clearing on day 1. It takes 10 days. They finish on day 11, which becomes the start date for the footings crew. Real-world logic translated directly into mathematical notation. This is why network diagrams work. They are just the physical reality of construction, written down in numbers. If the forward pass was the outward journey, discovering the earliest possible schedule, the backward pass is the return trip. We are now going to move from right to left through the network and answer a different but equally important question. What is the latest an activity can start without delaying the project? The formula: LS equals LF minus duration. We are now subtracting. We are working backward. We know when the project must end, that is our late finish for the last activity, and we subtract durations as we move left through the network to find the late start and late finish for every activity. In our example, the project must end by day 20. That is our deadline, our late finish for activity B. Footings has a duration of 9 days, so the late start for footings is 20 minus 9, which equals day 11. That late finish of 11 for footings now becomes the late finish for activity A, site clearing. And site clearing with a duration of 10 gives us a late start of 11 minus 10, which equals day 1. Now look at both nodes completely filled in. Site clearing, early start 1, early finish 11, late start 1, late finish 11. Footings: early start 11, early finish 20, late start 11, late finish 20. In both activities, the early times and late times are identical. That means these activities have zero scheduling flexibility, zero breathing room. They must start exactly on their early start date and finish exactly on their early finish date. In other words, these are critical path activities. Fascinating, isn't it? 2 simple formulas, and you can already identify which activities will sink the project if they are late. Now we put the forward pass and backward pass to work in a network where paths converge, where multiple activities feed into a single successor. And this is where the calculation requires a decision. At a merge point, which number do you use? Forward pass rule at a merge point. When multiple activities converge into a single successor, the early start of that successor is the largest early finish of all its predecessors. Not the smallest, not the average, the largest. Why? Because your successor cannot begin until all of its predecessors are complete. So you must wait for the last one. In our example, Node C finishes on day 24. Node D finishes on day 19. Both feed into Node E. What is the early start of Node E? Max of 24 and 19 equals 24. Not 19, even though that would give us an earlier schedule. We cannot start Node E until both C and D are done. D may be done on day 19, but C is not done until day 24. So we wait for C. Backward pass rule at a split, called a burst. Point. When we move backward from a single activity to multiple predecessors, the late finish of each predecessor is the smallest late start of all its successors, not the largest, the smallest. Why? Because each predecessor must finish in time for the earliest successor to begin. In our example moving backward from E, late start of E is 24. So late finish of C equals 24, and late finish of D also equals 24. Both predecessors must be ready by day 24. Here is a real-world scenario that every construction professional has encountered: the waiting game. You pour concrete. The concrete needs 3 days to cure before you can strip the forms. So you sit there, watching concrete, thinking about your life choices. The question is, how do you model that 3-day waiting period in your network? It is not an activity. Nobody is doing any actual work during those 3 days. The curing process is happening, but you are not consuming labor or equipment for it. You are just waiting for chemistry to do its thing. In AON, the solution is called a lag. A lag is a minimum waiting period placed directly on the relationship line between two activities. In our example, we put the number 3 in a circle on the arrow between place concrete and strip forms. That tells the scheduling software, after concrete is placed, wait 3 days before allowing form stripping to begin. Elegant, simple, accurate. The sticky note in the corner gives us a critical advantage of AON over AOA. Arrow networks, AOA, cannot do this directly. In AOA, to model a curing delay, you would have to invent a fake 3-day activity called wait for concrete to cure, or something equally awkward. The activity does nothing. It has 0 resources. But it has to exist just to make the math work. In AON, the lag handles it cleanly, right on the relationship line. A lead, by the way, is a negative lag. It accelerates the start of a successor, allowing it to begin before its predecessor is completely finished. Leads are theoretically allowed, but rarely used in standard construction scheduling, as they can create logic problems if not carefully managed. Let's dig deeper into lags, because there is a subtle trap that catches even experienced schedulers. We call it the software pitfall. Scenario: Activity A, concrete placement, finishes on a Friday. Activity B, stripping forms, uses a standard 5-day workweek calendar. You have specified a lag of 2 days for the curing requirement. Here is the trap. If the software is calculating based on calendar days, the 2-day lag from Friday would land on Sunday. But Activity B runs on a 5-day week, so it naturally starts on Monday regardless. The software has just automatically given you a 2-day weekend lag. But what if you needed exactly 2 working days of curing, not 2 calendar days? You would actually get 4 calendar days, the weekend, instead of 2 working days. This is not hypothetical. On real projects, calendar mismatches in lag calculations have caused schedules to be incorrect by days or even weeks. The fix? Either enter the lag on a 7-day calendar to get exactly 2 calendar days of waiting, or create an explicit dummy activity, wait for concrete to set, with the exact duration and calendar you need. It is slightly more work, but the schedule is accurate. This is one of those subtle details that separates schedulers who understand the underlying math from schedulers who just click buttons and hope the software is right. The software will do exactly what you tell it to do. Make sure you are telling it the right thing. Now we arrive at one of the most powerful features of AON, the 4 logical relationship types. If AOA was a single-speed bicycle, AON is a 10-speed. This slide is your gear guide. Relationship 1. Finish to start, FS. The most common type. Activity A must finish before activity B can start. Our example: concrete cannot be placed until formwork is built. A finishes, then B starts. This is the classic, intuitive, universal relationship. If the entire world of construction used only this one relationship type, we would still be okay. But we can do better. Relationship 2. Start to start, SS. Activity B cannot start until activity A has started. Our example: excavation cannot start until site clearing begins. Notice they can run simultaneously. The clearing crew works out ahead, and the excavation crew follows right behind. SS relationships are perfect for modeling this kind of train convoy logic in fast-track projects. Relationship 3. Finish to finish, FF. Activity B cannot finish until activity A has finished. Our example: landscaping cannot finish until the driveway is finished. Both activities might be running at the same time, but one cannot wrap up until the other wraps up. Think of final punch list items that depend on other work being complete. Relationship 4. Start to finish, SF. Activity B cannot finish until activity A has started. Our example says it all: almost non-existent in construction. This relationship type is so rare, so counterintuitive, and so rarely applicable to physical construction sequences that many experienced schedulers have never used it once in their careers. Know it exists. Do not lose sleep over it. Now, let's combine relationship types with lags to model some very specific real-world situations. This is where scheduling starts to feel genuinely powerful. Finish to start with lag, our left example. Activity A is construction of a footing. Activity B is placing the steel column on that footing. The relationship is FS with a lag of 10 days, because concrete needs 10 days to cure before it can carry the load of a steel column. So the formula is early finish of A plus 10 equals early start of B. The footing finishes, we wait 10 days for the concrete to gain strength, and then the steel column crew shows up. This is a very common construction scenario. Concrete curing lags appear constantly in foundation work, slab work, structural column work. Mastering the FS with lag relationship is not optional. It is essential. Start with lag. I'll write example. Activity A is delivering steel columns. Activity B is erecting those steel columns. The relationship is SS with a lag of 2 days. Why? Because the erection crew needs some inventory of delivered columns to work from. They cannot erect a column the moment it rolls off the truck. They need 2 days of delivered material before they can start productive erection work. The formula, early start of A plus 2 equals early start of B. 2 days after delivery begins, erection can begin. And while delivery continues, erection follows right along behind. The footer of this slide says it beautifully. Scheduling must account for physical reality, like concrete curing times or overlapping delivery and installation. The schedule is not an abstract mathematical model. It is a representation of the physical world. Every number has a physical meaning. We are going into advanced territory now. Negative lags. Yes, negative. If a positive lag slows things down, a negative lag speeds things up. And used carefully, negative lags allow you to model overlapping work sequences with extraordinary precision. Example 1. Negative finish to start lag. Activity A is steel erection. Activity B is painting. The relationship is FS with a lag of -5 days. What does that mean? It means painting can begin 5 days before steel erection is completely finished. The formula, early finish of A minus 5 equals early start of B. The steel erection crew is about 50% complete, and the painting crew starts work on the sections already finished. This kind of overlapping work compresses the schedule significantly. Example 2. Negative finish-to-finish lag. Activity A is building a retaining wall. Activity B is painting that wall. But the client only wants 75% of the wall painted. Painting should finish 7 days before wall construction is done. The relationship is FF with a lag of -7. Formula, early finish of A minus 7 equals early finish of B. The wall and the painting overlap, with painting finishing a week before the wall is fully complete. The bottom line says it perfectly. Negative lags allow for highly precise overlapping of distinct trades to compress project timelines. This is the scheduling equivalent of a master chess player thinking 3 moves ahead. When you see a complex, fast-track project schedule with dozens of overlapping trades, all managed without chaos, this is the technical mechanism behind it. Let us work through a concrete, pun absolutely intended, example of a negative finish-to-finish lag in action. Node C has an early finish of 18. It connects to node E with a finish-to-finish relationship with a lag of -4. Step 1. Calculate the early finish of E using the FF relationship. Early finish of E equals early finish of C plus the lag. That is 18 plus -4, which equals 14. Step 2. Calculate the early start of E. A finish-to-finish relationship dictates the finish times first. Once we know when E finishes, day 14, we subtract its duration of 7 to find when it must start. Early start of E equals 14 minus 7, which equals day 7. So node E, early start equals 7, duration equals 7, early finish equals 14. The negative FF lag has caused E to finish before C finishes. The two activities overlap. E finishes on day 14, C finishes on day 18. Painting the wall is done before the wall is completely built, because only 75% of the wall is being painted. This is the logic a negative FF lag enforces. It says, I do not care when A finishes completely. I only want B to finish relative to that. And because it is a negative lag, B finishes before A does. The software handles this calculation automatically once you input the relationship correctly. But understanding what the software is doing allows you to catch errors, verify outputs, and explain your logic to clients and attorneys. Advanced Scheduling Lesson. And we are going to start with a cautionary tale. The SS relationship alone, start to start, is powerful, but it has a dangerous flaw when used by itself without a companion relationship. Look at the top example, marked as the error. Clear and grub takes 10 days. Excavation takes 4 days. We apply an SS lag of +2, so excavation can start 2 days after clear and grub starts. That puts excavation starting on day 3 and finishing on day 6. But clear and grub does not finish until day 10. Excavation finishes before its predecessor. The schedule shows excavation wrapping up 4 days before the site has even been cleared. On paper, the logic is satisfied. The SS constraint is met. But physically, it makes no sense. The excavator would be trying to dig ground that has not been cleared yet. The fix, the bottom example, marked with the check mark. Combination relationships. We use both an SS lag of +2 and a finish-to-finish constraint. The FF constraint ensures that excavation cannot finish until clear and grub finishes. Now both the start and the finish of excavation are constrained. The front end is controlled by SS +2. The back end is controlled by FF. The successor cannot sneak in early and finish before its predecessor is done. The final point on this slide is crucial. These relationships are binding in one direction only. You can exceed the lag, you can take longer than required, but you absolutely cannot violate it. The lag is a minimum constraint, not a maximum. The constraint says, wait at least this long. It does not say, and hurry up to finish on time. And here it is. The concept that the entire course has been building toward. The critical path. Definition: the longest continuous path in a network from start to finish. It dictates the project completion date. Read that again. The longest path dictates the completion date. Not the average path, not the most important looking path, the longest one. Why? Because the project cannot be complete until all paths are complete. And the longest path is the last one to finish. So the minimum possible project duration is the duration of the critical path. You want to finish the project faster? You have to shorten the critical path. There is no other way. Look at our network. The red highlighted nodes, 1, 2, 4, 5, form the critical path. The gray nodes, 3 and 6, are on a shorter, non-critical path. They are shown in gray because they have scheduling flexibility. You could delay them somewhat without delaying the project. 3 golden rules. 1. Every network has at least one critical path. Some have more than one. We call these concurrent critical paths. 2. Any delay on this path directly delays the entire project. Day for day, delay for delay. 3. Activities on the critical path typically have 0 total float. 0. No wiggle room, no safety net, no buffer. If they slip, the project slips. One more concept from this slide: driving versus non-driving relationships. A driving relationship directly controls the start or finish of the next activity. A critical path is a chain of driving relationships from project start to project finish. When you audit a schedule and find the critical path, you are tracing the chain of driving relationships. Beautiful. Now we have the formula that lets us find the critical path mathematically, without having to trace every path manually. The magic number is called total float. Total float equals late finish minus early finish, or equivalently, late start minus early start. 2 equivalent formulas. Pick whichever one you find more intuitive. What does total float mean? It is the amount of time an activity can be delayed without delaying the final project completion date. Think of it as the scheduling safety margin for each activity. Look at our example. Activity A. Late finish equals 11. Early finish equals 11. Float equals 11 minus 11 equals 0. Activity A is critical. It has no flexibility whatsoever. Activity B. Late finish equals 15. Early finish equals 10. Float equals 15 minus 10 equals 5. Activity B has 5 days of breathing room. You could delay Activity B by up to 5 days, and the project would still finish on time. The critical path is the specific sequence of activities where total float equals 0. Connect all the 0 float activities from project start to project finish, and you have found your critical path. It is automatic, it is mathematical, it is unambiguous. And the warning: if a critical path activity is delayed by 1 day, the entire project is delayed by 1 day. This is not a probability statement. This is a mathematical certainty. Managing the critical path is the most important job of a project scheduler. We are going deeper into the float rabbit hole, and it is worth every minute. Because total float is not the only kind of float. There are 3 kinds, and each one tells you something different about your scheduling flexibility. We already know total float, the total flexibility before the project end date is affected. Now meet free float. Free float: how much an activity can be delayed without affecting the early start time of its immediate successor. Not the project end date, just the next activity in sequence. Free float equals the early start of the successor minus the early finish of the activity. The example at the top? Node C has a duration of 9, early start of 9, early finish of 18. Node E, its successor, has an early start of 18. Free float of C equals 18 minus 18 equals 0. Even though C might have total float of 5 because the project has slack, C cannot delay without pushing E's early start. These are different constraints. Now, independent float, absolute slack. The time an activity can be delayed when its predecessor finishes as late as possible and its successor starts as early as possible. Independent float equals early start of successor minus late finish of predecessor minus duration of activity. This is the most conservative form of float, the only flexibility you can use with zero impact on either your neighbor before you or your neighbor after you. The note at the bottom of the slide says it perfectly. Independent float is usually 0 in practice, which is fine. The formula matters for understanding schedule sensitivity even when the number comes out to 0. A beautiful visual summary of our two most important float types. Keep this slide in your mental reference library. Total float, shown as the long bar with the activity block and the dashed total float extension beyond it. The formula, TF equals late finish minus early finish. The meaning, the maximum time an activity can be delayed without pushing the project end date. This is the broadest, most permissive form of flexibility. Free float, shown as the gap between activity A's block and activity B's block, with the free float zone clearly marked between them. The formula, FF equals the minimum early start of successors minus the early finish. The meaning, how much you can delay this activity without forcing any of your successors to start later than they otherwise would. And the critical note at the bottom, which I want you to memorize. Free float is always less than or equal to total float. Always, without exception. This makes intuitive sense. The constraint on your immediate neighbor is at least as tight as the constraint on the end of the entire project. And here is the sharing problem, a subtlety that trips up many schedulers. If a predecessor consumes its shared total float, it strips that float away from all downstream activities. Float is a shared resource on a path. If activity X uses up 3 days of its 5-day float, all activities downstream on that path now have only 2 days of total float instead of 5. Float is not personal property. It belongs to the path, and everyone on the path shares it. Now we get into a topic that is absolutely critical for real-world project management, but rarely covered in basic scheduling courses. The types of float based on when the work can happen within the available window. Total float tells you how much an activity can be delayed, but it does not tell you when, during that delay window, the work must happen. Can you start late and work straight through? Can you start on time and finish late? Can you pause and resume? These questions are answered by the type of float restriction. Unrestricted float. The work can happen anywhere within the window. Start early, start late, take a break in the middle, resume. As long as you stay within the total float boundary, you are fine. Maximum flexibility. Start restricted float. The work must start at the early start date. You cannot delay the beginning, but you have flexibility in when you finish. You can work at a reduced pace or take breaks after starting. Finish restricted float. The work must finish by the late finish date. You can start whenever you like within the window, but you cannot be late to finish. Maximum end date discipline. Double restricted float. Both the start and the finish are fixed at their early and late boundaries, respectively. The work can be interrupted in the middle, but the bookends are nailed down. The bottom line from this slide is important for project managers. Total float is not always a free pass to delay. In precedence networks with complex relationships, float can be locked to specific boundaries. Understanding which type of float you have for each activity prevents scheduling mistakes that look valid on paper but violate physical project constraints. Now we leave the mathematics and enter the most human part of scheduling, the politics. Because float is not just a mathematical concept, it is a resource. And like all resources on a construction project, people argue about who owns it. The scenario: a non-critical activity has 5 days of total float. The contractor decides to use those 5 days. No problem mathematically. The project end date is not affected. But who does that decision affect? Enter our two stakeholders. The senator's view, or the final completion date perspective. This person cares about one thing only: will the project finish on time? As long as the end date is not affected, anything goes. Use all your float, rearrange your schedule, do whatever you need to do. As long as the building is done by the contractual completion date, everything is fine. The governor's view, or the early start times perspective. This person is anxious. They know that using float now means you have no buffer later. What if something unexpected happens in week 12? If you have already consumed your float in week 3, there is nothing left to absorb the shock. The project immediately falls behind schedule the moment any unforeseen issue arises. The takeaway, shown in the red box at the bottom: float is a resource. Project managers must carefully choose when and how to consume it. This is not just technical advice, it is contractual advice. Many construction contracts specify who owns the float: the contractor, the owner, or the project as a whole. If the contract says float belongs to the project, the contractor cannot use it for their own convenience without risking a claim. Here's a reality check. You can build the most perfect network diagram ever created. Every relationship correct, every lag validated, every float calculation verified. The critical path is identified. The schedule is airtight. And then reality raises its hand and asks, do you actually have enough workers to execute this? Because a schedule that requires 40 carpenters on Tuesday, when you only have 15, is not a schedule. It is a wish list. And wish lists do not build buildings. This is where resource leveling comes in. The unleveled schedule at the top of the slide shows the resource utilization chart in red, peaks shooting up far above the maximum resource limit line. On those peak days, you would need far more workers than you have available. Impossible to execute. Resource leveling takes those non-critical activities, the ones with float, and shifts them in time to smooth out the resource demand. Instead of having everyone on the project working simultaneously in week 3, you stagger the activities. Crew A works in weeks 1 through 4. Crew B starts in week 2. Crew C starts in week 3. The work gets done, but the resource demand stays within the available capacity. Look at the leveled schedule in blue at the bottom. The bars are flatter. The peaks are gone. The utilization stays below the maximum resource limit for the entire project, and
Critically, the project end date has not changed. We used the available float to shift activities without extending the critical path.
The key phrase, resource leveling, manipulates non-critical activities or extends durations to smooth daily resource demands without extending the overall project timeline. When it is necessary to extend the timeline, that is called resource-constrained scheduling, and it often requires negotiating with the owner. Let us address the elephant in the room. Because if you walk onto any construction job site in the country and you look at what is hanging on the trailer wall, you will almost certainly see a bar chart, a Gantt chart, not a network diagram. So why are we spending an entire course on network diagrams? Look at the left side, the bar chart. Time-scaled, simple, and excellent for field presentations. Look at the right side, the network diagram. Not time-scaled, but it shows true logic dependencies and computes the exact critical path. Here's the truth. Both tools have their place, and the best project managers use both. Bar charts are communication tools. They are intuitive. Your subcontractors can read them. Your owners can read them. Your field superintendents can read them. They are the language of the job site. But bar charts have a fatal flaw. They lack mathematical logic. A Gantt chart can show you that activity B starts after activity A finishes, but it cannot tell you why. It cannot tell you what happens to the rest of the schedule if activity A is delayed by 3 days. It cannot identify the critical path. It cannot calculate float. It is a picture of the schedule, not the mathematical engine behind it. The network diagram is the mathematical engine. It is where the critical path is calculated, where float is determined, where resource conflicts are identified. And from that network diagram, the scheduling software generates the bar chart as an output. The warning note is priceless. Forcing network logic onto a time-scaled bar chart often results in an unreadable spaghetti schedule. Do not try to make a network diagram look like a bar chart. They serve different purposes. Use the right tool for the right job. And here we are, the last slide. The PM checklist. 3 bullet points that distill everything we have covered into actionable professional guidance. Number 1. Teach AOA. Practice AON. Understand activity on arrow for historical context and theory. It teaches you the fundamental logic of network scheduling in a way that builds deep intuition. But when you leave this classroom and walk on to your next project, use activity on node exclusively. That is where the industry is. That is where the software is. And that is where you need to be. Number 2. Leverage software. Modern networks are far too complex for hand-drawn calculations. Even a modest commercial project might have 300 activities with dozens of relationships, multiple calendars, and resource assignments. No human being can maintain that manually and stay sane. Learn Primavera P6. Learn MS Project. Understand the math behind them, which you now do, so that you can audit what the software produces and catch its errors. Because software does exactly what you tell it to do. If you tell it something wrong, it will calculate the wrong answer very efficiently. Number 3. The ultimate goal. A clean network links the work breakdown structure directly to cost estimates, cash flow projections, and defensible claims analysis. That is the power of a properly constructed network diagram. It is not just a schedule. It is the backbone of your entire project management system. It connects the technical work to the financial world and to the legal world. When a project goes into dispute, and some projects do, the network diagram is often the most important document in the case. A clean, logical, well-maintained network is your defense. A sloppy, inconsistent, poorly constructed network is the other side's best argument against you. So go forth, build clean networks, calculate with discipline, manage the critical path relentlessly, and build great things. Thank you for your time, your attention, and your commitment to this course. See you on the next one.